Hello and a warm welcome. I am Armin Trost, Professor for Organizational Behavior at the Furtwangen University in Germany, and this is my course on social research methods. So now, hello everybody. This time we're going to talk about analysis of variance. And this method to test hypotheses is in particular useful when you compare group means. This is something that you very often have in experimental designs. We were talking about this when we were talking about experiments. You have an independent variable, right? And that could be even nominal, right? You compare different groups where the independent variable is really nominal, right? You compare engineering students with social science students. It's nominal scale, right? So, and then you have one dependent variable, one, okay? So and that's something, as I said, that you have always in very often in experimental designs. You have a control group, you have an experimental group. In this case, you have two groups. Sometimes you have three groups because you have maybe a control group and two experimental groups. So what you do in the end, you compare the differences between these different groups. And you basically compare the means of the dependent variable across these different groups. Now let's say you have depressive patients, people who are depressive, and you want to compare different therapeutic methods. Let's say one is just with pharmaceutical, one is with cognitive behavioral therapy, and the third group gets nothing, something like this, right? So you have three groups, and then after a while you measure before and you measure afterwards, and you measure, let's say, based on the Beck depression inventory, you measure how well the people are doing. Okay, and then you find a difference maybe. And the ANOVA now is the analysis of variance, is about looking whether the difference is really significant. The meaning of the difference, the interpretation of the differences, the meaning must happen based on the averages as such. So in this case, you would expect that for maybe a certain therapy, depression is lower than for another type of therapy, and even more, there must be a difference, should be a difference be expected compared to having no therapy at all, right? So the analysis of variance does just tell you whether the difference is significant, and does not tell you anything about the direction of the outcome. That's something which is worth to mention here. Maybe one term that I would like to introduce later in this episode is the MANOVA. Yeah, it's like ANOVA with an M in the beginning. M stands for multiple, because sometimes you not only have one independent variable, but maybe you have two or even more. Then we talk about a multiple analysis of variance. That's just a kind for the beginning. We will come to this point later in this episode. And I would like to start with a little example that we walk through. And it's something that is very heavily discussed since many years and months. It's the idea that different generations differ with regards to their preferences, their way of thinking, and behavioral style, and whatever. So there is a difference between the differentiation between Generation X, which are those who are born between 1965 and 1979, Generation Y, those who are born between 1980 and 1994, and there is Generation Z, born between 1995 and 2015. So don't ask me where these terms come from. Does not matter here. Generation X, Y, Z. And you find incredible literature and TED Talks and all the like talk about this huge difference between people who are born in different times. Also, in the area I work in, human resource management, organizational behavior, there is always this debate whether you should treat people who are of certain generation differently than other people. Yeah. And so the question now is there really a difference? And the idea here is that there is a variance between these groups. And when we talk about the variance between the groups, we talk about the differences in the averages, right? So in my picture here, you find 3 bell curves, and you can tell from the visual shape here that there is some overlap, but there is also a difference. When you just look at the mean, then yeah, there is a difference. But there is also a variance within the group. I mean, when you look at all people who belong to Generation X or to all people who belong to Generation Y or to Z, you will find that within those generations, people really differ. Okay, so this is the first thing that I want you to understand. It's very important to see this difference, that there is a difference between groups and variance within groups. And what we very often focus on in all our debates and everything is the variance between the groups, right? I mean, it's like when you look at intercultural studies, for instance, Gerd Hofstede, for instance, I mean, he found out that people in different cultures think differently. They have different values. And when we look at this, and my students, they also learn this. They learn that people differ depending on the culture in which they grew up, which probably is true to some extent. But it's wrong to say that when you belong to a specific culture, that you are all the same. Not all Japanese people are the same, not all German, not all American, not all African. No, there is a big difference also within a culture. So that's the first thing that I want you to understand, that there is this variance between groups, but there's also a variance within groups. And this is something that we now compare in a analysis of variance. The null hypothesis would be there is no difference. Actually, there is no difference. Even when you found some differences in your little study, in fact, there is none. What you found is just random. Yeah? So the null hypothesis says there is no difference in the real average between those different groups. And the alternative hypothesis is to say, well, there is a difference. There is a true differences in the mu. Yeah? When you calculate, when you estimate the mu for every group, there is a difference. Yeah? Mu generation X is not equal to mu generation Y. It's not equal to mu generation X. Z. So, okay, so this is null hypothesis and alternative hypothesis. So I have some data here, some fictitious data from a fictitious survey. And now let's just assume you ask people from different generations one single question. You ask them, in your career, how many different jobs do you intend to have? I mean, that's something that is sometimes discussed. While in earlier generation, we assume that when you work at Daimler, you're going to stay with Daimler. That's at least in my region where I grew up. I mean, Daimler is close by here where I live. So, and you have one job in your life, right? Maybe two or three. But with the younger generation, well, they want to try out new things. They are more mobile and not so much stick to one thing. So we think that, well, they want to experience more than just one job. So, okay, I mean, that's maybe the idea. So in our little survey, we now get the results. And you find on my picture here, you find the raw data for 90 people in total. You have 30 people with Generation X, 30 people in Generation Y, 30 people with Generation Z, and you ask them all the same question. Okay, so now you can do, of course, a comparison based on the frequencies. Okay, how many people of Generation X said 2, 3, 4, 5, 6, and what did the people say of Generation Y, and what did the people say of Generation Z? So, and you compare this, right? But the easier thing that you would do is you would compare the mean. And this is shown on the right side on this picture. So you see, in this fictitious example, you have Generation X saying on average 4.23 jobs, while Generation Y said 3.6 jobs and Z said 3.87 jobs. So already based on those averages, you see a difference, right? And I mean, that's something that I explained when we were talking about bivariate statistics. Now we maybe could stop here and say, well, you see, there is a difference. And people from Generation X expect more jobs to have in their life than, for instance, people from Generation Y. There is a difference. And now based on the average, we can interpret, right, how these how the generation affect your intention to have a certain amount of jobs. So, but now the question is, is that random or not? So, and to understand now analysis of variance, we have to have a closer look. So we have to look at the components of a single value. Components of a single value. And in my picture here, you see the value of one single person, the answer of one single person. It's the value x, yeah, of somebody who belongs to Generation X, person 1, x, x1. Okay, x is the value, it has nothing to do with the generation. It's just the value x, yeah, as we put it in statistics. Okay, so when you look at this value, what's in that value? We assume that in this value there are three components, so to speak. We can say, well, in this value, the value is determined by the fact that the person who has responded to this question is a human being, right? And this overall tendency of somebody being a human being is represented by the total mean. We could also say this is the value people typically show when they are asked this question. Okay? And then there is another component which relates to the fact that somebody belongs to Generation X. You say, no, I'm not just a human being. I'm more than this. I'm a member of Generation X. So that's why I'm a little bit more higher. You're lower, right? Okay? The fact that I belong to this group affects that I'm above average, average, or lower than the average. Yeah? So I'm more than just a human being. I'm also a member of this generation. Okay? But your individual value is even more than this. It's you say, okay, I'm a human being. And I belong to generation X. That's why I'm a little bit less or higher than typically. But I'm also an individual. I am myself. I'm me. So, and that's why I'm a little bit more, a little bit less. So you have these three components, so to speak. And the explained deviation based on this hypothesis is that, yeah, of course, you differ because you belong to a certain generation. But the fact that you vary because you're an individual, that is not part of this theory. And that is something that we name the unexplained deviation. Okay? So that's something you need to consider. In every measurement, there is something that is due to the overall tendency, and there's something which is due to the fact that you belong to this treatment, to this group, and then there is some noise. Yeah, we could name it noise, some error, something which is not explained, right? Yeah. Okay. That's important to see. And coming from that idea, we differentiate different variances. And we do this based on the sum of squares, the sum of squares. And I've shown you in this picture, I showed you the formulas for the different sum of squares. We have the total deviation. Yeah, this is how people overall differ, right? I mean, not everybody is asking the same in the same way. So there is a variance in total, yeah, right? So we can calculate this total variance of all 90 responses. And there is also an explained variation, which is due to the different groups. That's the variance between the groups. But there is also a variance within the groups, which is not so much explained by the model. Okay, so we have total, explained, and unexplained. Well, in this picture, I've showed you the formulas, and of course you will forget the formulas after this episode, and I also forget, but I just wanted to mention them here. What I did is I did a little analysis based on these data, and you can see how these sum of squares can be calculated. Okay, and I don't want to spend too much time on this. But maybe if you want, you can pause a little bit here and look at this table. It's very enlightening to have a closer look at these results and see how these different cells differ. It's very, very simple math at the end. And what you find in the end is the total sum of squares is equal to the sum of squares between plus sum of square within. So in this example, the total sum of squares is 50.1. The sum of squares between is 6.07, and the sum of squares within is 44.03. And the sum of square between plus the sum of square within make up the total sum of square. So you see, you split the overall variance of all responses into two separate types of variances. Those between, which we can explain based on our hypothesis, there is a difference between different groups, and the sum of squares variance within these different groups, which is not so much explained. Okay, and of course there are very simple formula to calculate these different variances: total variance, variance between groups, variance within groups. I did this in our example. So here the variance, the total variance is 0.85. The variance between is 3.03, and the variance within is 0.77. So what we now do is, with this in hand, we calculate something that we call the F value. We simply, and it's a very simple idea, we divide the variance between by the variance within. And what we want, if we really believe there is a difference between generation, we want that the variance between is big and the variance within is small, because the variance within, that's something that we cannot explain without theory. That's the noise. Yeah? We want to see a big variance between and a small variance within. I mean, the opposite would be to have a little variance between. They don't really differ, but they vary much within. Then there would be nothing there. So we want to have, in the end, as big as possible F value, right? This is something that we want to have. And now it's something that you might not understand in this moment, but now you have to simply consider the so-called degree of freedom in the counter, and you have to look at the degree of freedom in the denominator. That's something that you need to do. You say, okay, to reject the null hypothesis, probability must be probability of the alpha error, we were talking about this in the last episode, should be less than 5%. And then there are F value tables. They simply exist. You find this in the internet. You find this in every statistic book. You simply look at the degree of freedom, and then you look at the significance level, and then you look at what must be the F value in that regard. And now you see that our own F value, 3.93, is higher than the one proposed in the table, 3.15. So we can reject the null hypothesis. That's it. Okay, I know it's a little bit fast and you cannot follow on everything probably, but I mean, sometimes you can pause and think, but that's the overall idea of analysis of variance. Now, let's take some time to talk about multiple analysis of variance. And this is something that we do when we have more than one independent variable. This is something that we very often have. For instance, two independent variables. Yeah. For instance, in the area I work, organizational behavior, human resource management. For instance, there is always this question of does money have an effect on performance, right? Variable pay, for instance, pay for performance, contingent reward, and so on. It's a very interesting field. And when we look at the research there, we can say that for simple tasks, money really increases performance. If you say the more you work, the more money you receive, if you say so, then you receive better performance. And that's true for simple tasks. But for very complex tasks, it's the opposite. With complex tasks, that can kill motivation. That turns intrinsic motivation in an extrinsic motivation, and performance goes down. So you see also on this picture, there is not this just one effect. There is a kind of, we name this an interaction, right? Statistical interaction. You say, whether something increases or goes down depends on another variable. Okay, and that's the interesting part of a two-way MANOVA where you have two independent variables, that you cannot only look at the individual effects of the independent variables, but also at their interactions. And what you do with a MANOVA is you very often look at visualization of your results, just like I've done here with graphs, for instance. And I have different scenarios here, different typical outcomes that you find. So, for instance, with the example on the top left corner, here is an interactive effect. You really can see that there is an interaction between independent variable 1 and independent variable 2, but there is also an effect with variable 2. Yeah, the red one is higher than the than the plaque one, right? And when you look at the second example on the middle upper side on this picture, you see that there is a strong effect of independent variable 1, but no effect of independent variable 2, or maybe just a slight effect. While with the next one, next example, you have a strong interaction, yeah, really this cross, but there is no effect of independent variable nor an effect of the there's no effect of independent variable 1 nor an effect of independent variable 2, but there is a very strong interaction, right? And with the next example, there is a strong effect of both independent variable 1 and independent variable 2. There is no interaction, not at all. But both show individually a strong effect. And with the last example here, on the bottom side in the middle, you see no effect at all. Right? So that's very interesting to look at individual effects of both variables, independent variable 1 and 2, but also at the interaction. That's the fascinating idea about two-way MANOVA. And I would like to conclude with a very typical output from a statistical procedure. This is how it looks like. This is how you would publish it in your article, in your report. And you see all the different components. You see the effects of independent variable 1, independent variable 2, and you see the interaction, and you see the variance within the error and everything. You see also the degree of freedom, but most importantly, you see the F values and you see the significant level. So when you look at the significant, you can say that significance is with independent variable 2 very, very low. So you can really say that here you should better reject the null hypothesis. Independent variable, the null hypothesis that independent variable 2 has no effect, you can reject. Yeah. You could also reject the null hypothesis that there is no interaction between independent variable 1 and independent variable 2. But you might reject the null hypothesis that there is no effect of independent variable 1. So this is a typical output. I wanted to add this part of MANOVA to this entire chapter of analysis of variance. So that was much. I hope you took something home. So thank you, and we see us next time.